Coming up on Dr. Kiki Science Hour, we're asking the big questions of the universe to Dr. Sean Carroll from Caltech. That's up next on Dr. Kiki Science Hour.
Netcasts you love.
From people you trust.
This is Twit. Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki Science Hour with me, Dr. Kiki, episode number 99, recorded on Thursday, June 9th, 2011. Time for Dark Matters. This episode of Dr. Kiki's Science Hour is brought to you by Netflix. Watch thousands of TV episodes and movies streamed to your PC, Mac, or TV instantly. Plus, get DVDs by mail in about one business day. For your free 30-day trial, go to netflix.com/twit. Welcome, everyone, to another episode of Dr. Kiki's Science Hour. It's episode 99. It's almost to 100. It's pretty fun. Pretty fun. Next week's going to be a lot of fun. So we'll talk about that a little bit at the end of the show. Right now, it is time for the usual. One topic, 1 hour, one expert. So I hope you're all ready to get dirty because we are talking about the big questions of the universe with Dr. Sean M. Carroll. But first, some science headlines for the week. What's going on in science this week? We are number one. Well, at least our current time of carbon dioxide emissions is. The current amount of CO2 being released into the atmosphere is about 10 times greater than the amount released during the last similar period of climate change, also known as the Paleocene-Eocene thermal maximum. You can read about that over on Ars Technica if you want. They've done a nice write-up of that study. As jellyfish are becoming more common in the warming waters around our globe, we might find them actually to be a significant factor in shifting the carbon balance of the oceans. A recent study found that jelly excrement and mucus release tended to favor the growth of certain bacteria that release carbon dioxide into the atmosphere. So that could be a pretty bad feedback cycle there. Jellyfish poop leading to carbon dioxide. The breakthrough could be on researchers at MIT have created semi-solid flow batteries that could allow you to fuel up instead of charging up by simply replacing the charge-carrying fluid when your battery starts running low. And they're calling it Cambridge Crude, I think is the name that they're calling it right now. Officially published in Nature Physics, scientists at CERN have successfully trapped antimatter particles for just over 15 minutes, which will make the hard-to-study stuff a lot easier to study. Did modern humans come from Asia? A team of scientists from the nation of Georgia think they have evidence that puts the Caucasus Mountains, the Caucasus, yes. I don't know where I went with that one. Caucasus Mountains at the center of the dispersal of the Homo lineage nearly 1.75 million years ago. The Joint Working Party on the Discovery of the Elements has spent 3 years looking at the evidence and decided that U.S. and Russian scientists have successfully discovered elements 114 and 116, which will be called flerovium and moscovium, respectively. Evidence for elements 113, 115, and 118 were rejected. And reviews of data from the Cogent and Dama Libra dark matter detectors suggest that there is a dark matter signal that peaks in late April to early May. Maybe we will see dark matter yet. Maybe, but maybe that's something we can talk about in the rest of the show. And so hopefully that's a topic that we can discuss with our guest today, along with other questions like, what is time? Is it real? Is it really real? What about gravity? Dark matter? Where are we anyway? This place we call Earth. Here to discuss these questions and more is Dr. Sean Carroll Dr. Carroll is a theoretical physicist at Caltech, where he does research on theoretical aspects of cosmology, field theory, and gravitation. He's especially interested in inflation, the arrow of time, and what happened at or before the Big Bang. He's done work on dark matter and dark energy, modified gravity, topological defects, extra dimensions, and violations of fundamental symmetries. He also wrote a book on cosmology and the arrow of time called From Eternity to Here, The Quest for the Ultimate Theory of Time, which I have right here. And he recorded a set of lectures on cosmology for the Teaching Company. He started blogging back in 2004, and you can find his writings about physics and other topics at Cosmic Variance. So without any further ado, welcome, Sean. It's great to have you on the show.
Hi, Kiki. It's great to be here.
So what got you so interested in these topics of cosmology, dark matter, dark energy, the arrow of time? What just tickled your interest bone?
I was a kid when I started getting interested in these things. I used to hang out at the public library in Bucks County where I was growing up, and I just loved the science section and the physics section. And particle physics and the Big Bang, and I thought that this is what I wanted to do for a living. And so now here I am. And in particular, I think the arrow of time touches on things that we all know about, right? We experience time every day, and yet when we think deeply about what this means, it ends up leading to questions in cosmology and what happened at the Big Bang.
I'm having a few breaks there. Sorry, I don't know if it's my bandwidth or it's probably my connection on this end. So leading into the questions of the arrow of time, we all experience time in the manner of present is where we are right now. We can think about the past and remember the past. We can't remember the future, but we can plan for it. And somehow we continue to move forward in this manner where the present then becomes the past and we move into the future. How is our universe designed that is the way things work?
Well, it's interesting. Everything you say is correct. We live in the present, we remember the past, we predict the future, and it's very different, right? There's no way that anyone would confuse yesterday with tomorrow. It's just so obviously different. But then when we think about how time works more and more, when we study it as scientists, when we learn more about it, we end up with some equations, the equations that govern Newtonian mechanics or quantum mechanics or general relativity or whatever your favorite theory of physics is. And in those equations, there's no difference between the past and the future. Time is there. Time is a parameter that tells you what moment of the universe you're talking about. But the difference between moving toward the past and moving toward the future isn't anywhere to be found in the fundamental laws of physics. So that's the mystery that we're faced with. Clearly, our everyday experience calls the past and the future two utterly different things, so much so that we think the past has happened, right? The past is real. There's no choice about it. But we get to cause things in the future. We get to make choices that choose between different possible futures in ways that we don't get to choose between different possible pasts. But that way of thinking is just completely alien to the laws of physics. In the laws of physics, there's a past, a present, a future. They're equally real. They're equally predictable on the basis of any of the other ones. So that's what physicists are trying to do, to reconcile how we think the deep down laws of physics work with how we just experience everything in our lives.
Do you think that there's a big difference between what you say is experience and personal experience, how our brains see the world versus the way it's put together and what physics can tell us about it?
Well, I think it's not yes and no, because our brains are part of the particular universe that we live in. I don't think that our brains are any different than, let's say, a computer and a computer memory or other recording devices, right? I mean, you can take a photograph, and the photograph will represent something that happened in the past. You don't have any photographs that represent things that will happen in the future. So it's not that our brains are special because we're human or we're conscious or we're biological. It's just that the ways that we have of accessing the past and the future are very different. We have memories of the past, records of the past. And ultimately, that's because of what we call the arrow of time, because we're embedded in a universe where entropy is increasing, where the universe is going from being very, very orderly to very, very disorderly. So it's not the laws of physics that say you can make a camera that records pictures of the past but not of the future. It's the particular configuration of the universe that we find ourselves in. And that's kind of something that we're trying to understand better and better.
What kind of experiments have really been the I guess the standard, the gold standard experiments for defining time in our universe?
Well, there's a whole great question about what is time, right? And some physicists are so ambitious that they want to abandon time entirely. They think that it's a waste of something to be talking about time. But I'm not among them. I think that time is very useful. It helps us be in the right place at the right moment. So measuring it, however, is still something very tricky. One very, very good notion, one very good definition of time is what clocks measure. But then you have to define a clock. What does that mean? And the answer is that clocks are just things that do the same thing over and over again, right? If you have an ordinary an analog watch with a second hand and a minute hand and an hour hand, every time that hour hand goes around once, the minute hand goes around 12 times if you have a regular kind of watch. And that's predictable. The same ratio of revolutions of the big hand to the little hand is absolutely universal. And likewise, we have things going on in the sky. Every time the Earth goes around the sun, it rotates 365 times. So we are lucky enough to live in a universe that is full of clocks, that is full of things that are vibrating and rotating and revolving and changing their relationships in a regular, predictable way. The reason why quartz watches are really good is because the quartz crystals vibrate at a very, very predictable frequency. It doesn't matter what the temperature is, what the pressure is. Your quartz vibrations are very, very reliable. And so the world is full of these little clocks, and that's how we tell time. We have something that goes back and forth in a predictable way. The story I like to tell is Galileo. He was bored in church one day, and he was watching the chandelier rock back and forth above his head in the church. And he realized that the chandelier was a good timekeeper. It was reliable. And how did he test that? By counting the number of rockings of the chandelier versus his own pulse. So your pulse is more or less predictable. The chandelier is very predictable. And comparing these two things to another tells you that they're both good clocks. You there? Still here?
Okay. Yeah, sorry, it broke up for a second. I wasn't sure if you were finishing or if you were taking a quick, brief pause. I don't know what's going on with the connection, unfortunately. Okay, so we've got these lots of clocks in our world. So our brains, I know that within our own bodies, we have timekeepers as well, not just the beating of our hearts, but we have chemical timekeepers that the suprachiasmatic nucleus that starts our body clock and gets us working in a certain way. So, I guess as you're alluding to, as creatures of this universe, we are basically we are built to record time and to understand time, but really understand it.
That's right. We experience
we
time.
We don't really understand it. Yeah.
We there's plenty of things that you can experience without understanding, that you can deal with, right? I don't know how to use the remote control. I don't know how that works really on my TV, but nevertheless, I can use it. And time is the same way. We use it all the time. Our bodies, like you say, are full of different kinds of clocks. That is, things that do predictable things on a regular basis. And in fact, it's a famous quote from Saint Augustine, who said that, I know what time is until you ask me. And then I'm at a loss. Then I have no idea what time is. And that's exactly the situation that we find ourselves in. But of course, as scientists, this is not going to make us happy. We're not going to be satisfied with being able to use a profound concept like time without knowing exactly what it is. And so it's one of the great examples where trying to understand something better at a deeper level has made it more surprising rather than more clear. The more we think about how time works, the more mysterious it becomes, because the deep down laws don't seem to match our everyday experience in a simple way. But of course, they do match somehow. So when something seems mysterious to us, that means that it's our job to work harder at it and to understand it better.
In terms of using time as in part of science, we exist in what physicists have defined as the fabric of space-time. And I keep hearing about people trying to do research, whether it's empirical or theoretical studies, to determine whether we can travel in time to the future, go to the future, or be able to move to the past. Is time travel actually a possibility? And I've also heard of individuals claiming that time is not one of the dimensions of our universe, but is actually just kind of a byproduct. Where do you sit with all of the different perspectives that people have come across?
Well, time travel is a very interesting question, and it is absolutely possible. Yesterday, I moved forward in time 24 hours, and here I am right now. Going toward the future is something that we can all do. We move toward the future 1 second per second, 1 minute per minute. When people are really interested in time travel, what they want to do is change the rate, right? They want to go into the future faster. So you could just put yourself in suspended animation and do this, right? That's kind of cheating because you're not really moving any faster. You're just not noticing it. Whereas Einstein told us that there are, in fact, ways to move faster into the future. If you zoom off close to the speed of light and then zoom back, or if you visit a black hole and hang out right close to the event horizon for a while and then come back here, either way, you will jump into the future. You will experience less time than the people who stayed back here on Earth did. But you can't go back. You can only go to the future, and you can go to the future faster. The real trick to time travel, what people really care about, is could we visit the past? And the smart money is that no, you probably just can't visit the past. The time is really a one-way street. But we're not sure. This is something that physicists are thinking about, have been working on, haven't quite completely nailed that one down yet. And the way that they're doing it is to try to come up with ways to travel to the past. Einstein, again, told us that we can warp space and time, that we can bend space-time itself. So you can at least imagine bending it so severely that it bends into a loop, that you personally can just march forward in time as far as you are concerned, but then you can end up in your own personal past. So you're getting older and older and older, and then you find yourself meeting with yourself from 10 years ago. This is a hypothetical idea. It's, like I said, probably not possible, but we're not sure yet. It's still an open question. So I wouldn't bet money on it, but I think that it's a very intriguing idea, and it's another sign that we don't understand the fundamental laws of physics quite as well as we would like to.
Yeah, would something like that, warping of time, warping of space to be able to space-time to be able to bend it into a circle. The only thing that I understand currently is things with great mass bend space-time. They bend the fabric of space. Would it be something like a black hole, or that would be necessary to do that?
Something of that ilk, basically. Einstein tells us that every piece of matter and energy bends space-time. That is what gravity is. Gravity is a manifestation of the curvature of space and time, so it's caused by stuff. It's caused by matter and energy. But if you're talking about warping space-time so much that it actually literally loops back on itself, you clearly need to have a tremendous amount of energy packed into a small area. So it's either going to involve a black hole or something equally dramatic. And the ideas that people talk about are wormholes, which are little tubes connecting different regions of space-time, or perhaps cosmic strings, which are a sort of another kind of defect from the early universe. But one way or another, literally tremendous astrophysical levels of matter and energy would need to be brought to bear and manipulated in exactly the right way if you wanted to have any hope at all of traveling backward in time. You would not hop into a phone booth and have it just happen.
Unfortunately, Doctor Who is not supported by science at the current understanding.
Yes, but of course, his technology is much more advanced than ours, so I can't promise you, yes.
Right. Okay, I need to take a quick break to thank our sponsor. So I will get back to the conversation. We've started talking a little bit about gravity, which I think is really interesting because there's some big questions about gravity even coming up in current research and hypothetical ideas that are out there. So without, I'd like to take this opportunity to thank Netflix. This episode of Dr. Kiki Science Hour is brought to you by Netflix. Netflix delivers movies to your home, and that saves you time, money, and hassle. We all like a hassle-free life, don't we? You can instantly watch thousands of TV episodes or movies. Like you can have them streamed directly to your PC or your Mac, or you can have them streamed to your TV if you have a Netflix-ready device like an Xbox 360, a PS3, Nintendo Wii, or even a Roku or a Boxy Box. You can also get DVDs by mail in about one day if that's how you like to get your movies delivered, and you can watch as many movies as you want anytime you want. And there are no late fees and no due dates. So those DVDs you don't have to worry about getting them back in time. One movie that's available to watch instantly, it's actually a series that you can watch. You can just go straight there, is The Hitchhiker's Guide to the Galaxy. Not the movie, but the series that was produced by the BBC. Cast is a wide cast, and it was created, the book, based on the book by Douglas Adams. It's a lot of fun, very quirky. It kind of gets us at this idea of traveling through space, time, all the rest, and asks a big question, the question to the universe, which we all know the answer to, I hope, by now. But I'm not going to say it. I might ruin the ending for you if you haven't heard it. So anyway, Hitchhiker's Guide to the Galaxy, I recommend it. It's a lot of fun. It's an alternative to reading the book, seeing it acted out on the screen, at home, the comfort of your own sofa or your office chair at your desk, if that's what you're trying to do. You can instantly watch this movie or choose from thousands of TV episodes and other movies when you register for a free trial membership. Just go to netflix.com/twit. Be sure to sign up for your free trial at Netflix. That's netflix.com/TWIT. We thank Netflix for their support of Dr. Kiki's Science Hour and Twit. Now back to the show. Is there any validity to anything in The Hitchhiker's Guide to the Galaxy, Sean? Are we going to step over things here if we don't take something about that book seriously?
One of the great lines is that space is very big. And that's very true. He got that one right. Most of the other things are fantasy, but space is big, yeah.
It is really big. So we're talking about this giant space. We have our universe. We're within the Milky Way galaxy, within this universe. And we're trying to understand the entire universe kind of by proxy a lot of times. But here we can figure out what gravity is. We have Newton's laws. We have the basic laws of physics that we're trying to put together. We have a standard model of physics. Yet sometimes things aren't quite lining up. And so gravity, I think, is very central to this. Time and gravity. What is gravity?
Well, Einstein told us that gravity is a manifestation of space-time itself. So before Einstein came along, we thought that gravity was a force of nature. Most people would still say that. We talk about gravity, we talk about electromagnetism, there are the nuclear forces, and that's okay for a rough and ready understanding of what's going on. But at a deeper level, Einstein realized that gravity is different than the other forces, because the other forces have some things that they pull on and some things that they don't, right? If you think about electromagnetism, an electron has a negative charge, a proton or a positron has a positive charge, and a neutron has no charge at all. Whereas for gravity, there isn't anything with no charge at all. Everything feels gravity and everything creates gravity in the same way. So on the one hand, this helped Einstein invent his theory of relativity, because he said we can think of gravity as a feature of space and time itself rather than as a force moving through space-time. On the other hand, it's extremely helpful to astronomers and cosmologists, because if everything is affected by gravity, then by measuring the gravitational fields of the universe, you can find everything that is in the universe. There's no way for things to hide. That is, as long as there's enough energy, as long as there's enough matter in that stuff, you can find it by looking at how it affects the universe. And of course, this is not just conjectural. This is why we think there are such things as dark matter and dark energy.
Right. So we can find gravity, we can measure gravity, but when we actually get to the question of what causes gravity, I mean, we know that gravity comes from matter, that that objects with mass have more larger gravitational pull or forces than objects with lower masses. But is there a graviton? Are we going to be searching for that particle, or is the gravitational force a byproduct of things? Is it something that is coming? Is a byproduct that's hitting our universe from a parallel universe?
No, there's a graviton. There is. Everyone who thinks about this believes that. We've not detected it directly, but the graviton is to gravity just like the photon is to electromagnetism. So if you were, a 19th century physicist studying electricity and magnetism, you would think that there's something called the electric field, something called the magnetic field, and there's something called light. And one of the great discoveries is that light is just a wave moving in the moving in the electro and magnetic fields. And then the 20th century comes along and adds to that picture quantum mechanics. And that's really where it became clear how you can get a particle out of that wave. Quantum mechanics says that if you look at waves in the right way, you can resolve them into individual particles. So in gravity, we have a field. We have the gravitational field, the curvature of space-time. We have waves in that field. We haven't detected gravitational waves directly. They're trying to do that at LIGO and other observatories. But we've detected their effects. There was a Nobel Prize to Hulse and Taylor for finding that gravitational waves caused the energy to be lost in a binary pulsar system. So we know that the gravitational waves are there. Einstein predicts them. We've seen their effects. What we haven't been able to do is to resolve those gravitational waves into individual particles, into individual gravitons. But it would be much, much more surprising if there weren't gravitons than if there were. The gravitational waves are just the classical versions of gravitons. It's just that gravity is so weak as a force. It's so feeble that the effect of one graviton is almost impossible to imagine detecting. We can detect photons because compared to gravity, electricity and magnetism interacts much more strongly.
So we're still waiting for the technology and the right experiment to be able to detect these things.
It's not even something you would really want to wait for. It's not going to happen within our lifetimes. The numbers are just far, far too weak to detect a gravitational field. The one way of thinking about it is every time you stand up, there's a fight going on between gravity and electromagnetism. And the electromagnetism is a small number of chemical reactions happening in your muscles.
Right.
And the gravity is every particle on Earth is exerting a gravitational force on you. And yet your body wins, right? The electromagnetic forces in your body are much stronger than the entire gravitational field of the Earth. And so that just really puts into perspective how weak gravity is. So a single graviton, or even some individual number of gravitons, no one is even imagining an experiment that would try to detect them.
It seems, though, with so much writing on this, on physicists saying this is what gravity is. Gravity is X, and building our understanding of dark matter, normal matter, baryonic, non-baryonic matter, dark energy, all these things around gravity, using gravity and our measurement of, and our visualization of gravity to be able to study these other things that we'd want to have something tangible in our hands.
That's right.
About
I mean,
gravity.
so there's no question that we want to test our understanding of gravity as well as we possibly can.
Yeah.
So, but that's a little bit different than in particular looking for gravitons. Gravitons
Right.
are a manifestation of quantum gravity, just like photons are a manifestation of quantum electrodynamics. But quantum gravity is just not really very relevant to either our everyday lives or to galaxies or the universe today, because gravity is just too weak. Understanding gravity at the classical level, was Einstein right, or do we need to do better? That's the question we need to ask to understand whether or not our inference of dark matter, dark energy, things like that is correct. And it's absolutely possible that gravity is the culprit, that there isn't any dark matter or dark energy, but instead that we need a better theory of gravity. The problem is, everyone knows this, and therefore people like me invent new theories of gravity. We propose tests of these new theories, and they fail. And Einstein's theory keeps passing its tests.
Yeah.
So
Right.
we've tested very, very precisely and in many different ways Einstein's theory of relativity. We haven't found any deviations from it yet. That's not to say that we shouldn't keep testing and trying, but right now the large preponderance of evidence says that Einstein was right, general relativity is the correct theory of gravity, and therefore we need both dark matter and dark energy to fit the data that we get from cosmological observations.
All right. Do you think Eric Verlinde has been getting, he's a theoretical physicist who's been getting a lot of, I guess there's a lot of hubbub about his recent ideas on gravity. He put a paper in the archive website. How do you think his ideas are panning out? Is there anything there?
I think it's a little bit too early to say. It's a very, very intriguing idea because what he's trying to do is to really break down gravity into its underlying pieces. And this is something that's very, very difficult, and it's been a challenge for several decades now. Like I said, we have this classical theory of gravity, general relativity given to us by Einstein. And as far as we can tell, it works in cosmology, in the solar system, in the galaxy, and so forth. But there's still some pieces missing. It can't be the final, ultimate answer. Number one, it's not compatible with quantum mechanics, and we know that quantum mechanics is right, so we need to do better. Number two, in the 1970s, Stephen Hawking demonstrated that black holes have entropy. He did, a series of magnificent calculations where he showed that black holes are not completely black, that when you include quantum mechanical effects, black holes actually give off radiation, and they will eventually evaporate. They have a temperature. And because of all these thermodynamic properties, you can actually say that the black hole has an entropy, which is great, and that is very helpful in understanding what's going on. But what it implies, when you have a big entropy, that implies there are a lot of states that look indistinguishable to you. The air in the room has a lot of entropy because you could rearrange the atoms in a lot of different ways and it looks indistinguishable to you. So what Hawking's calculations implied is that secretly a black hole is not just one particular configuration of the gravitational field. There are many, many, many different states of quantum gravity that all look like the same black hole. And we would love to know what those states are. What is this huge collection of possible arrangements of space and time, all of which look like the same kind of black hole? So what Verlinde is trying to do is to try to make steps toward that kind of answer. String theorists have had a lot of breakthroughs, actually, in trying to do better and better at answering that question. Verlinde has this particular new approach, which is cleverly called entropic gravity, because he relates gravity to entropy in a clever new way. It's a little bit vague right now. It's not something that you really put your fingers on and test it as well as we would like to. But it's sufficiently different and new and interesting that I think that people are very hopeful that we'll be able to push it forward and hopefully decide whether it's on the right track or not pretty soon.
Yeah, and I think one of the interesting aspects is he does come from deriving it from Newtonian equations, where starting with Newton's ideas drives it forward, kind of bringing everything together.
That's right.
Yeah, so very interesting. I'm excited to see more as people. I love watching these new ideas come out into the physics landscape and see how people respond to them and how they end up being accepted or denied by the population of physicists who are out there. It's always really interesting.
Well, and especially in this field, because sometimes it's stated that we have no data when we talk about quantum gravity. That's a little bit of an exaggeration, because we have a huge amount of data, namely every experiment that says that Einstein is right and every experiment that says that quantum mechanics is right. So we have this tremendous amount of constraint. You can't just do any old thing. You have to ultimately, if you're going to try to come up with a new theory of quantum gravity, it better be compatible both with Einstein's theory of gravity in the right regime and with quantum mechanics in the right regime. But that's not as much as we would like in way of clues that are pointing us to the right answer. So it's really a tremendously difficult project to just sit and think hard about how the laws of physics could possibly work in ways that would ultimately lead to gravity as we know it and quantum mechanics as we know it. It's much harder, and therefore it might not work. If you're doing particle physics or astrophysics or biophysics or atomic physics, you have systems that you can touch and observe, and you can make guesses and prove them wrong. When you're doing quantum gravity, it's almost all pure thought at this point, and that makes it much more difficult.
Yeah. In terms of gravity and dark matter, can you talk a little bit? Research right now, there was the story that I brought up at the beginning of the hour. Maybe the detectors are finally getting a signal. So far, with years of dark matter research, actually the particle physics side of it, trying to detect dark matter, there's been nothing. These detectors, the massive data that's been coming in, scientists have said, nope, no signal for dark matter, but finally there might be a signal. How does gravity play into dark matter, and where are we on the dark matter story?
Well, we've made a lot of progress over recent years, but still there's a long way to go. So dark matter was first hinted at way back in the 1930s when Fritz Zwicky at Caltech noticed that galaxies within clusters were moving faster than they should if they were just to be held together by their own mutual gravity. There needed to be more stuff in the galaxies, in the clusters of galaxies, than we knew about. But of course, for that, it could always just be ordinary matter that was just hidden in between the galaxies, matter that we didn't see. It became more clear in the 1970s when Vera Rubin noticed that galaxies themselves had more gravity in their outskirts, in their outer regions, than could possibly be accounted for by the gas and dust and stars in the galaxy. So people began to take seriously this missing mass or this dark matter problem. And then it became even more serious when people studied the early universe, and they were able to use the fact that the early universe is a nuclear reactor. In the early universe, protons and neutrons are fused together to make helium and other elements. And the amount of helium that you get out of the early universe tells you very precisely how much ordinary matter there is in the universe, the total amount of regular stuff, the total amount of atoms, helium, hydrogen, and so forth. And that total amount is much less than you need to account for the gravity that we observe in the universe. So by now, there's essentially no question that there is something called dark matter and that it is not ordinary matter that is just dark. It's some new kind of particle, some new kind of feature of physics that is beyond the standard model of particle physics. So you'd like to know, you'd like to see, well, can we make it? Can we detect it in the lab? Can we produce it in a particle accelerator? And right now, literally this year, we're at the point where it's becoming realistic that we can either make it in a particle accelerator or that we can detect the dark matter that is going through us here on Earth, just the ambient dark matter in the galaxy, occasionally bumping into our laboratory experiments. So, like you said, there's a couple of experiments right now that have sort of tantalizing hints for dark matter. I don't think that there's any consensus. There's certainly no strong consensus that these experiments are right. Some people think that they're right. They're certainly promising and intriguing. Others are very, very skeptical. We're not yet at the point where we have more than enough data to draw any firm conclusions. But it's absolutely possible that a year from now we will. So I think it's very, very exciting that we're at least on the possible cusp of turning dark matter into from a placeholder that, here is matter that we don't know what it is, into something where it's this particle, we have now found it, and we're trying to learn how it fits into the bigger picture.
Yeah, in terms of looking for particles, how do you detect something? How do you detect something? This is just a methodological question that you think is there, but you don't really know what it's going to be, what particle it's going to be.
Well, that's why it's hard. I mean, that's why this has been a challenge for years now. What happens is, dark matter is pretty abundant. So if our ideas are right, then in every sort of coffee cup worth of space right here in this room, there's about one dark matter particle, or maybe 10 or 100 dark matter particles. So they're passing through all the time. They're moving at 100 kilometers per second. So they're passing through your body at an incredible rate. But they don't interact very strongly. That's why dark matter is dark. It doesn't interact with ordinary photons very well.
Right.
But we hope, we're not sure, but we hope that it interacts with the nuclear forces, with the weak nuclear force in particular. That's why the favorite dark matter candidate is called a WIMP, a weakly interacting massive particle. So that means that most of the time the dark matter particles just go through you, but every once in a while, a dark matter particle will bump into a nucleus and deposit some energy there. So that's what you're looking for. You're building a very, very sensitive detector so that a neutral particle, one that doesn't interact with photons, with electrons, will just occasionally bump into a nucleus inside your experiment. The problem is that there are other particles that do that, like neutrons and neutrinos and things like that. So you build your experiment deep underground, you try to shield it from all the other things around, and then you try to sort of calibrate it so that you need exactly the right energy to make this detection happen, and you rule out stray interlopers from other particles that we know and love. So that's where all the effort is. That's where all the technological wizardry comes in. These experimenters need to be very, very good so they can distinguish the dark matter interactions they're looking for from the ordinary matter interactions that we already know are there.
And it seems like the recent study, the data that they're looking at the is it Dama Libra in the Cogent? Dama Libra and the Cogent detectors, it looks like they've got a very specific signal that they're starting to get, like you said, not with a lot of significance, not that there's a large amount of data, but there's this interesting signal that seems to peak in the springtime.
Yes, that's right. So there's two strategies for looking for dark matter this way. One is that you can just try to be as quiet as possible. You can really rule out all of the noisy particles by just building your detector way underground, rejecting all of the things that don't look like dark matter, and hoping that you find the one or two events that would really be dark matter. The other technique is a very clever one. It says, let's admit that we're not very good at distinguishing between ordinary interactions and dark matter interactions. But as the Earth goes around the sun, it's going through either a headwind or a tailwind of dark matter. There's an average velocity of the dark matter in the vicinity of the sun. And so as the Earth moves, it's either moving with the dark matter or against it. And that changes the rate of interactions. It's really just like the wind is in your face or at your back. So if this is right, if you're detecting dark matter, you don't need to be that careful about distinguishing between ordinary interactions and dark matter interactions. You just need to say, is there, as the year goes by, do the total number of interactions go up and down? Is there an annual modulation? So there are two experiments, like you say, that are looking for this. There's the Dama experiment and the Cogent experiment. And Dama, there's absolutely no question that they are seeing something. It's incredibly statistically significant. It's been there for years. There's no question they're seeing something. The question is what they are seeing dark matter, or is it something else? The bad part is that there's lots of things that vary on a 365-day time scale, like the thickness of the atmosphere above your experiment that shields you from cosmic rays, or just, the air conditioning in your laboratory varies on that time scale. So you would like to do it somewhere else. And so the Cogent experiment is a separate experiment, completely independent, looking at the same technique. They were originally hoping to rule out what Dama was claiming to find, and instead they seem to see a hint that looks similar to what Dama is claiming to find. It's not nearly as significant yet. It's just barely beginning, but it's suggestive. It might be something that is very real. So, and this is something they're collecting data relatively quickly. There was a fire in the laboratory, so they were shut down for a while, but they're back on their feet, and hopefully the new data will come in soon and will get more significance, or it will go away.
And if we find dark matter, if we actually find the signature of dark matter and say, okay, this is the frequency, or this is the signature that dark matter, where you find dark matter, what is that going to do for physics?
Well, for some particular physicists, it's a trip to Stockholm to pick up their Nobel Prize, because that's a huge step forward. Particle physics, which is, a small part of physics overall, but an important part, has been, in some sense, stuck for a while now. And it's been stuck not because the experimenters or the theorists are not smart. It's because the theorists from the 60s and 70s were too smart. They built this theory, the standard model of particle physics, which continues to fit all the data, even when we get more and better particle accelerators. Ever since the mid-1970s, all that our particle accelerators have done is collected more data that fit the standard model of particle physics. Dark matter doesn't fit the standard model of particle physics. There's no candidate particle in the standard model that really fits the qualities that you need from dark matter. So we know that dark matter is outside the standard model. The standard model can't be the full story, but we don't know very much at all about the particular properties that dark matter has, other than that it's hard to detect. So it could be very, very light. It could be very, very heavy. It could interact through different forces. There's a million things we don't know about it. So as soon as you detect it in the laboratory, you rule out a huge number of theories, and you favor some small number of theories that actually predicted that kind of interaction. If we're lucky, what you learn about the dark matter particle is something you didn't expect. Maybe its mass or maybe its interaction is a little bit different than you were expecting. That's always what scientists want to see, because that gives you a clue. It's not just something that fits in with your ideas. It's something you pushes you past the ideas that you had. Maybe the interactions are different. Maybe it fits in with other particles. Maybe it surprises you in what its abundance is. So we'll have to see what the data come back and tell us. But once you know it's there, then you can really focus in on studying it in detail, and that'll be great.
Is it going to, it's not part of the standard model, but will it support any other theories, like extended string theory, or are there any other models that are out there that dark matter would be a part of, that it would give support to?
Absolutely. In fact, it will give support to every model. That's the problem. Since everyone knows there is dark matter, every theoretical physicist who invents a new theory of particle physics part of what they do, part of the employment guidelines are that you predict the existence of dark matter, right? Because that will fit into what we know is true about the universe.
Yeah.
So the problem is that you creep up on this kind of knowledge. It doesn't all come at once. So when you do decide that you've discovered the dark matter, you might have a fairly good idea of what its mass is, and you might have some hope of an idea of what its interaction is. But that's not that much, right? I mean, there's many different theories: supersymmetry, extra dimensions, string theory, technicolor, new generations of quarks and leptons. There's many different kinds of theories that could predict particles with those properties. So then we'll begin the narrowing down process. So, okay, given that there's this dark matter with this mass and this interaction, what does that tell us about something else? Where else can we go look? What should we be looking for at the Large Hadron Collider or at the Tevatron at Fermilab? So it'll really be very, very useful to physicists because it will tell us in large extent what to do next, but it will not answer all the questions we have. We have to keep working for that.
There's always more questions to ask.
There always are.
I know. In terms of dark, not just dark matter, but we're looking for these signatures. You know, dark matter's here. It's part of our universe. We're trying to figure out how to detect it so we can confirm its existence. But we know that there's more in our universe than what we can see, for sure. When we start smashing atoms at each other, so the gold ions, different things that we're smashing together, say at Fermilab or the Large Hadron Collider, is there a possibility that we might create dark matter, that we might see it as in part of these giant collisions that we're producing? Or are we just going to see other particles, hopefully the Higgs boson or others?
No, it's absolutely a target that particle accelerators are shooting for to create dark matter. It's not easy because the dark matter doesn't interact very strongly. So it's actually one of the more difficult things to find at a particle accelerator. What would happen is two particles come together and they smash into each other with a certain energy, and they create a bunch of particles, and what you notice is that the total energy in the particles that were created is less than the energy of the particles that went in. And the reason why is because you also created some particles that you didn't detect after you created them. They could be neutrinos or they could be dark matter particles. So if you think you have a good handle on the kinds of particles you know and love, and your experiments are telling you that you're missing energy because of some new kind of thing, something that doesn't fit into the particles you know and love, that's the kind of signal you're looking for to detect dark matter. And it's a huge program at particle accelerators. And there's also a third way. So that's two ways of getting dark matter. One is an underground lab, another is a particle accelerator. The third way is that you look in the sky, and occasionally a dark matter particle and a dark matter antiparticle will hit each other and annihilate into some high energy gamma ray. So the Fermi satellite experiment right now is a gamma ray observatory that is scanning the sky, looking for these high energy photons that could come about because of dark matter annihilating. And once again, because it's the messy real world, not a pristine theorist's playground, there's lots of gamma rays out there, and many of them are from lots of different very ordinary things, from pulsars, from black holes, from high-energy processes in the interstellar medium. So there's no question that there are gamma rays out there. The question is, are any of them from annihilating dark matter? And so there's, again, an intense program between observers and theorists trying to figure out what is the most efficient way we can use the data that we're collecting to see whether or not it really implies that there's dark matter responsible for some of these photons that we're getting.
That's really neat. Now, we're getting towards the end of the hour. I know that you've worked with Fermilab and done research with people there. How do you feel about Fermilab closing? They're getting some really interesting data, or at least some papers that have been coming out recently suggesting another particle that the LHC has not yet confirmed.
That's right. So just to be very, very clear, so that my physicist friends don't get mad, Fermilab is not closing. Well, the Tevatron is shutting down. Yes. So Fermilab is a laboratory. The Tevatron is their big high energy particle accelerator. So even when the Tevatron shuts down, there will still be other physics experiments going on at Fermilab, such as dark matter experiments and neutrino experiments and theorists and so forth.
Right.
So Fermilab is not going away. In fact, Fermilab would love to be the site for the next big particle accelerator if we ever get one. As far as the Tevatron is shutting down is concerned, it's a little bit bittersweet. You know, every big experiment like that has to end at some point. The other big particle accelerator we used to have here in the United States was at Stanford, at the Stanford Linear Accelerator, and that no longer exists. It was dismantled, and that they now have a photon beam there that is doing other interesting kinds of experiments. So you can't be too nostalgic about great experiments that have done a tremendous amount of work over a tremendous amount of years once they're superseded by other great experiments. On the other hand, you know, like you say, the Tevatron has not completely outlived its usefulness yet.
No.
In a world of an infinite amount of money, I would certainly love to keep the Tevatron running. We don't have an infinite amount of money. I'm not the boss of the money when it comes to physics or science in the world, so I don't get to choose where it gets spent. Certainly, it's a great experiment, and if we could find the money, we should absolutely keep it running. That's probably the best I could say.
All right. Well, thank you very much. For people out there who are interested in hearing more about Dr. Carroll's adventures in physics, his theoretical thinkings, he's written a book, as we said at the beginning of the hour, From Eternity to Here, The Quest for the Ultimate Theory of Time. And you can, of course, get this book in the old-fashioned paper variety. It is also available in digital formats so that you can probably read it on your Kindle if that's something that you're interested in doing, if that's the way you consume your reading material these days. Additionally, you can go to Dr. Carroll's website, which is preposterousuniverse.com, and it's there are links there to his book. There are links to his blog, all sorts of information about Dr. Carroll and ways that you can contact him if you are interested. You can find him. He is Sean M. Carroll on both Twitter and Facebook. So there are interesting things that he has to say all the time, and you can follow those tweets and Facebook updates if you're so inclined. Sean, it's been just fabulous talking to you, and I have lots of other questions, but unfortunately, we're at the end of our hour. You've got some great things to say, and I know that my co-host on This Week in Science, Justin, would probably want to argue long and hard with you about gravity and dark matter from his armchair physicist perspective. But it's just been great to get to hear what you have to say about these topics and to hopefully gain. Find a way for everyone out there to gain a little bit more understanding of the universe around us and how physicists are thinking about it and where we are right now in our understanding of it.
Well, thanks very much for having me on. It's always a great pleasure, and it's our universe. We all live in it, and we're all made out of the stuff. So I think that everyone should indulge their curiosity about how it really works at a deep level.
That's right. Even if that curiosity is simply a Mentos and Diet Coke experiment.
That's fine. Exactly.
Thank you very much. I hope you have a great evening. Everyone out there, thank you for listening to or watching, depending on how you're consuming this media, this episode of Dr. Kiki's Science Hour. I will be back next week. In the meantime, you can find me online. You can Google me. I'm Dr. Kiki on Twitter and Facebook and all the social media type places. You can find Dr. Kiki's Science Hour on the Twit network if you go to twit.tv/Kiki, and you can download past episodes. You can find them on YouTube as well if you want to watch them in video. And we're on iTunes, so you can figure out how you want to watch this or listen to this, or I guess that's all you can do is watch or listen to it at this point in time. But you can go to iTunes and pick your favored method of consuming this and do so. If you are interested, next week, it's our 100th episode of Dr. Kiki's Science Hour, and I think we're going to have a party. It's going to be a science party. The details are not all confirmed yet, but we'll find some fun things, games and experiments and, get people to say a few things. We like people saying sciencey things. I guess we should have toasts, cocktails, toasts, all sorts of fun stuff. But anyway, if you have ideas for our science party or science celebration for our 100th birthday, send them to me. I am Dr. Kiki at drkiki.tv, or you can tweet me, Dr. Kiki. And that's it. I'll see you next week. Thanks for tuning in to my Science Hour. Remember, all I do ask is 1 hour a week, and I do hope that this hour made your world a whole lot more interesting.